Hello, in this video we are going to go over the solution of the problem 743, and for solving this problem I'm going to use the algorithm Dijkstra. And for using the algorithm Dijkstra, first we need to know how this algorithm works. So there is a very good video on YouTube that explains the details of that, so I put the link underneath of this video that I highly recommend you to watch that video first and then come back here. So I'm going to use the exact same example that is explained in that video. So that example is this one. So I have a network like this that has 6 nodes, 1, 2, 3, 4, 5, 6, and they are connected, and direction of the connections is clear, and we are going to see how long does it take to visit each node. For example, for node 2, 3, 4, 5 in the table, at the end, so we have 45, 45, 10, 25, and infinity. Nothing reaches to 6. And we want to know how to implement this algorithm in Python. Let's start. Okay, the function that we are going to have called network delay time here. So the input to that is times, and that is this array. And you see the first row 1, 3, 45 is this one. 1 is connected to 3 with 45. And the second one is 1, 2 with 50. And 1, 4 with 10, and so on. So this shows all of the connections to us. Capital N is the number of nodes. We have 6 nodes here. Capital K is where the source is, where we are starting. So that is K equals 1. So we are starting at node 1. Then to show the connections in a nice format, so I'm creating a dictionary called graph by using this for loop. So we fill out that graph dictionary, and you can see that is here. So for example, for node 1, so you see here node 1 is connected to 3 with 45, and then it's connected to 2 with 50, it's connected to 4 with 10. Then we go for the second node, node 2. Node 2 connected to node 4 and with weight 15, and node 3 with weight 10, and so on for all of the nodes. Then we defined another dictionary called distance. And distance, we say that is the same length. So we have 6 nodes, and all of them are infinity. At the beginning, we say, okay, distance to everything is infinity. And also, we update that distance at the starting point k to 0. So here in my distance now, you see 1 is infinity, 2 infinity, 3 infinity. And then here, distance of 1 is 0. So we know that at the point 1, our distance is 0 because that is the starting point. The rest of them is still infinite. And also I have a list that shows me the visited nodes. Right now the length of that is n plus 1. We don't care about the first item because that is just the index, but all the rest of them, these things are going to turn true as we visit each node. Okay, let's go over the while loop that we have to see how we are calculating this table. So our goal is to create this table, and the value that is going to return that table for us is distance. So distance values are the values of the dictionary that we created. So we are going to return those values in a nice format. So if I run this, so you see I have this one, for example, is one while loop, the other while loop. At the end of each one, we are creating the rows of that table. So for example, at the beginning it's 0, 0 is for the starting point. That is not shown here, but you can imagine that is for the starting point. That is 50, 45, 10, infinity, infinity, 50, 45, 10, 25, infinity, and so on. Okay, so our goal is to create that one, and we are doing that in this while loop. Okay, for example, I'm right now at node 1, and for deciding should I go to 50, 45, or 10, at the beginning we put a node distance, a very large number. And then we decide and say, okay, is 50 less than infinity? And that is not in the scene. And say, yeah, this is 50, that is less than infinity, that is not in the scene nodes, and that is an accepted thing. So I add that and update my node list. Node list will be updated to 50, and node is updated to 2. So I say, okay, by now I should go here, but we are still in the for loop. So it says now node distance is updated to what? It's updated to 50. For the next one, we come and say that is 45. Is that less? Yes, that is 45. So we update node distance to 45 and I is 3. Now say, okay, no, it seems that I3 is better option, that is less. And then next time it's come and say, okay, no, distance I is 10. Is that less than 45? Yes, it is. So we update I to 4. So at the end, we decided to go to 4. So the next one will be 4. And if we print out the scene list, so we see that in that one we have to update the I4. So it is 0, 1, 2, 3, 4. Now this one is true. This node is visited. That is how we use scene list variable, so to update the visited nodes. And here we had in our statement that the new node that we decide that should not be a scene vertex. Okay. The other point for this loop is that you see I'm starting from a node -1. And if nothing happens here, so the node remains -1. And what happens here? The next line. So if it is negative, we are out of the loop. So the end of this algorithm is where nothing happens for the node. I'm at a node and every other node is already visited. So in that case, we break out of the loop. The other point is that I might get to the node here 6 is not connected to anything. If I look at my graph, 6 is not connected. We saw that the 5 is connected to 6, but 6 is not connected to anything. So in that case, so we are just going to skip those nodes and continue the while loop. Okay, if I print the node and graph of the node, so I see on the right side on the screen how these nodes are, what's the order we went forward. First, we visited node 1. When I'm at node 1, I have 3 options: node 3, node 2, and node 4. And then I visit node 4. I come here. You see, that is the line here on the table. And then we go for node 5. Then we go for node 2. Then we go for node 3. Node 6 we are not going to go. That is not going to be visited. There is no way we reach to node 6. Okay, now I'm at that node, for example 1. So I'm going to go and visit all of the neighboring nodes. For example, here you see I'm at node 1. I'm going to go and say I want to visit 3, 2, 4. At node 4, visit 1, 5. Node 5, 2, 3. Node 2, 4, 3. Node 3, we only visit 5. Okay, now we are going to see how we are updating each row. For example, I am here in the graph at node 4. We are in the first row, so we have 50, 45, 10, infinity, infinity. That is this distance here. And then we said, okay, 10 is minimum. We decided on the minimum value 10. That is node 4. We go for node 4. So for node 4, from the graph, we know that is connected to 1 with a cost of 10, and that is connected to 5 with a cost of 15. Okay. So then I say, okay, first let's visit the node 1 as a first neighbor. So I say the node neighbor with called n here, that is 1. The distance from that is 10, and the node itself that we are right now on that, so it's node 4. So I say, what is the distance of the neighbor? So we already saw that is 0 because that was our starting point. What is the distance of node 4? So 1, 2, 3, 4. That is 10. So I'm here at 10. Okay. Then I say the minimum of distance of n, which is 0, and distance of the node 10 plus the d. What is d? 10. So what is the 10 plus 10? That is 20. What's the minimum of that? That is 0. So minimum is 0 here. So if I want to update the distance of n, which is what we have already. And then we go for neighbor 5, and neighbor 5, the distance is 15, and the node that we are right now on that is 4. I have minimum of infinity and 10 plus 15. Which one is minimum? 10 plus 15, which is 25. We update the distance of 5 to 25. That is the second row on the table. This is how we update the values on the table. So let's go one forward. What is the minimum right now? Minimum is 25. That is node 5. You see node 5 is the next one selected. what node 5 is connected to. Node 5 connected to neighbor 2. Where is neighbor 3? Here, with cost 35. Okay, now we go for neighbor 2. Neighbor 2 distance is 20. I am at node 5. What is the distance at node 2, at neighboring node? That is 50. Here, we already calculated that. What is the distance at node 5 that I'm on that right now? That is 25. We already calculate that. And then what is the minimum between 50 and 25 plus 20? 25 plus 20 is 45. So we are updating distance of the neighboring 2 to 45. Right now my distance updated to 45. So here 2 is 45 on the third row. That is updated. So also for neighboring 3. Neighboring 3 distance is 35. No, we are at node 5. What is the distance of N3? N3 from the dictionary distance is 45. What is the distance of the node? Node 5. That is 25. 25 plus 35, what is that? 60. That is very large. So we keep still the distance N as 45. So this could be, our row will remain as for the 3, 45. That will be 45, 45, 10, 25. And we go forward and update each row. Okay, now see what we are returning for this function. We are returning a dictionary. So dictionary that we have for all of the values, we printed here. That is the row of that table. So 45, 45, 10, 25, infinity. So for this particular example, it asks us what is the minimum cost to visit all of the nodes. So you say, okay, the minimum for visiting all of the nodes, so it's 45. I need 45 to visit everything. Okay, so that's why we are returning that as all received signals here as the return. So we say what is the maximum of these values? That is 45. I need 45 to visit everything. So I will return that. But if one of them remains infinity, like this is particular example that there is no way to reach to the node 6, so in that case we are returning -1. So in that case, so I say I return all received signals if all received signals are less than infinity. Otherwise I return -1. Now let's talk about time and space complexity. We know that for Dijkstra algorithm, the time complexity is order of n to the power of 2 plus e. N is the number of nodes and e is the number of edges. So why we have n squared? Let's see here. So I have a while loop that in each loop we are going to see one of these rows of the tables. So for example, we see node 1 at the beginning, then node 4, node 5, and so on. And in each while loop, each block here, then I'm gonna go and check in this section of the algorithm. We are going to see for all of the nodes again. So I from 1 to 6, I from 1 to 6, I from 1 to 6. So that is how that resulted in n squared. Also, when I'm here at, for example, node 1, I'm going to check all of its edge connected to that. So here I have for node 1, node 3, 2, 4 connected. So node 1, 2, 3, 4 connected. For another node, for example, node 5, I have two nodes, node 2 and node 3. Because of that, I have this e number of edges here added. And space complexity is also order of n plus e. Because we created a giant dictionary at the beginning that I have n keys. So I have key 1, I have key 2, I have key 3, and so on for each node. But what is inside those keys? So then I have a list inside that shows all of the edges connected. For example, for key 1, so for key 1, I have 3 nodes. So not only I am creating n space for keys, I also should create e space for all of the edges connected to that. That's the reason we have n plus e. Okay, let's go over this algorithm for the final time. So we had this algorithm here that I'm creating this table. So at the beginning I had that graph, a dictionary. I put everything in that shows the connections. Then I have a dictionary that also shows the distance for each node, and I have that dictionary at the beginning 0 because I'm starting at 1. And then I have a while loop. In this while loop, at the first section it's for I, this section. So that is where we are deciding which element is minimum. And then the next section here, The next comparison minimum at the end is the one that we decide which one should be updated. For example, here 45 got updated in the third row by that, and at the end I'm returning the maximum of all of the distances, because we know we need a time that we can visit all of the nodes, and if we don't visit all of the nodes we return -1. Okay, thank you so much for watching this video.